Imagine standing on a quiet beach at night. The sand is cool beneath your feet, the air still, and above you, stretching from horizon to horizon, is a sky so clear it feels like you could reach up and brush your fingers against the stars. They don't twinkle so much as pulse, steady and ancient, like distant lighthouses blinking across an ocean of darkness. In that moment, you might feel small, not insignificant, just small. And that feeling, that quiet humility, is your first real encounter with scale. But here's the thing, your brain wasn't built to grasp what big really means beyond the reach of your arms, your voice, your daily walk. For most of human history, the world ended where the eye could see. A mountain range on the horizon, that was the edge of everything. A storm rolling in from the sea, that was the sky's full drama. Our senses evolved to navigate forests, rivers, and plains, not galaxies. So when someone says, "The Milky Way is huge," your mind tries to translate that into something familiar. Maybe the distance across a country, or the size of Earth, or the span of the solar system. But each of those comparisons collapses under the weight of reality. The Milky Way isn't just big. It operates on a scale that defies intuition, mocks analogy, and rewrites what distance even means. Let's start with something you know, Earth. Our planet is about 8,000 miles across. If you drove non-stop at 60 miles per hour, it would take you just over 5 days to circle the globe. Now, zoom out. The moon sits roughly 240,000 miles away. Light, a beam racing at 186,000 miles every second, takes just over 1 second to cover that gap. That already feels fast, almost magical. But now consider the sun. It's 93 million miles from Earth. Light takes 8 minutes to make that journey. So when you look at the sun, never directly of course, you're seeing it not as it is, but as it was 8 minutes ago. You're looking into the past. Still with me? Good. Because now we leave the solar system behind. The nearest star to our sun, Proxima Centauri, is about 4.2 light years away. That means light, traveling at its impossible speed, needs more than 4 years just to get there. If you tried to drive to Proxima Centauri at 60 miles per hour, you wouldn't arrive for over 40 million years. You'd leave Earth in the age of early mammals and return to find, well, who knows what. Civilizations would rise and fall thousands of times over. Continents would drift. Ice ages would come and go. And that's just to the nearest star. Now, hold that thought. Because the Milky Way isn't just a few stars scattered here and there. It's a swirling city of stars, so dense in places that if you stood on a planet near the galactic center, the night sky wouldn't be dark at all. It would blaze with light, as if perpetual twilight were painted across the heavens by a billion suns. Astronomers estimate our galaxy contains somewhere between 100 billion and 400 billion stars. Let's take the lower end, 100 billion. That's more stars than there are grains of sand on all the beaches of Earth. More stars than seconds that have passed since the first humans walked upright. But numbers alone don't convey scale. They're abstract, cold. What if we tried to walk across the Milky Way? Suppose you could step off the edge of our galaxy and stroll straight through to the other side at a comfortable 3 miles per hour. How long would it take? The Milky Way is about 100,000 light years across. 1 light year is nearly 6 trillion miles. So the full diameter is roughly 600 quadrillion miles. At 3 miles per hour, walking non-stop, no sleep, no food, no rest, it would take you about 20 quadrillion years to cross it. To put that in perspective, the universe itself is only about 13.8 billion years old. You'd need to repeat the entire history of the cosmos, every supernova, every galaxy forming, every moment from the Big Bang to today, over 1,000 times before you reach the other side. And yet, from Earth, the Milky Way appears as a faint milky band arching across the summer sky. That's it. No grand spectacle, no obvious majesty, just a soft glow easily washed out by city lights. For most people today, it's invisible. We've lost the night sky to the glare of our own making. But for ancient cultures, that band was sacred. The Greeks saw it as milk spilled from the breast of the goddess Hera. The Finns called it the pathway of birds, believing it guided souls to the afterlife. Indigenous Australians wove it into Dreamtime stories as a river of spirits. They sensed its importance even if they couldn't measure it. They knew it was more than just stars. They just didn't know how much more. This disconnect between what we see and what is lies at the heart of our struggle with cosmic scale. Our eyes give us a flat, two-dimensional view. Stars appear as pinpricks on a dome, all at the same distance. But in truth, they're scattered across unimaginable depths. Some are neighbors, others are so far they've been traveling toward us since before Earth existed. The Milky Way isn't a picture on a screen. It's a three-dimensional structure, a rotating disk, a central bulge, spiral arms winding outward like the grooves of a cosmic vinyl record. And we're inside it, like a single ant on a spinning carousel the size of a continent, trying to map the whole ride from the middle of the floor. That's why how big is the Milky Way isn't just a question of measurement, it's a question of perspective. It forces us to confront the limits of human perception and the power of human ingenuity. We can't step outside our galaxy to take a photograph. No spacecraft has traveled even a fraction of a percent of that distance. Voyager 1, humanity's farthest flung artifact, has been flying for over 45 years and has barely left the solar system. At its current speed, it would take 70,000 years just to reach the nearest star. So how do we know what the Milky Way looks like? How do we measure something we're trapped inside? The answer is patience, ingenuity, and a deep, stubborn curiosity that refuses to accept I can't see it, as it can't be known. Over centuries, astronomers have used starlight like sonar, bouncing observations off the darkness to build a mental map of our galactic home. They've tracked the motions of stars, measured their brightness, decoded their chemistry, and listened to the radio whispers of gas clouds swirling in the void. Piece by piece, they've reconstructed the shape, size, and structure of the Milky Way, not by seeing it whole, but by understanding its parts. But before we dive into that detective story, we need to reckon with something deeper. Why does size matter? Why should we care how big the Milky Way is? It's not just about bragging rights in the cosmic census. Understanding the scale of our galaxy reshapes our sense of time, place, and possibility. It tells us how rare or how common planets like Earth might be. It reveals the forces that sculpt stars and scatter the elements of life across space. It connects us to a story that began billions of years before we existed and will continue long after we're gone. And perhaps most importantly, it humbles us. In a world that often feels crowded, noisy, and urgent, the sheer scale of the Milky Way offers a kind of quiet liberation. Your problems don't vanish, but they find their proper size. Not as the center of everything, but as part of something vast, ancient, and astonishingly beautiful. That's not despair. That's perspective. And perspective is the first step toward wonder. So as we move forward, remember this: we're not just measuring a galaxy, we're learning to see with new eyes. Eyes that can look up at a faint band of light and recognize it for what it truly is: a river of stars, a home of unimaginable scale, and the stage upon which our entire story has unfolded. The journey to understand its size is, in the end, a journey to understand ourselves. And it begins not with telescopes or equations, but with a single, simple question asked under a dark sky: how far does this go? For thousands of years, the night sky was not a place to be measured. It was a canvas for meaning. Long before anyone thought to count stars or calculate distances, humans looked up and saw gods, heroes, animals, and ancestors woven into the dark. The Milky Way, that ghostly river of light, was never just a collection of distant suns. It was a bridge, a path, a scar, a river of souls. In ancient Egypt, it was the celestial counterpart to the Nile, flowing eternally through the heavens. In China, it was the Silvery River, the stage for the legend of the cowherd and the weaver girl, lovers separated by its luminous current. The Maori of New Zealand saw it as a canoe carrying spirits to the afterlife. These stories weren't guesses. They were attempts to make sense of something overwhelming, to give structure to the sublime. But slowly, quietly, a different kind of curiosity began to stir. Not just, what does it mean, but what is it? This shift didn't happen overnight. It crept in with the invention of writing, the rise of cities, the need to track seasons for planting and harvest. The sky became a clock, a calendar, a compass. And with that practical need came the first real measurements. Around 2,500 years ago, in ancient Greece, a man named Aristarchus dared to ask, how far is the sun? How big is the moon? Using nothing but geometry and the shadow of Earth during a lunar eclipse, he estimated the relative sizes and distances of the Earth, Moon, and Sun. His numbers were off, wildly so, but his method was revolutionary. He treated the cosmos not as myth, but as space that could be mapped with reason. Centuries later, another Greek, Hipparchus, took it further. He catalogued over 800 stars, ranking them by brightness, a system we still use today, called apparent magnitude. He noticed that some stars seemed to shift slightly against the background over the course of a year, a phenomenon we now call parallax. Though he couldn't measure it precisely with the naked eye, he suspected it held the key to distance. If you hold your finger up and close one eye, then the other, your finger appears to jump against the wall. The closer your finger, the bigger the jump. Stars do the same, but the jump is so tiny that you need incredibly precise instruments to see it. Hipparchus didn't have those tools, but he planted the seed. The sky could be triangulated. Fast forward to the Renaissance. The invention of the telescope changed everything. In 1610, Galileo Galilei pointed a crude tube with glass lenses toward the Milky Way and gasped. Where others saw a smooth, cloudy band, he saw countless individual stars, too faint and too numerous for the unaided eye to resolve. The galaxy is nothing else but a mass of innumerable stars planted together in clusters, he wrote. Suddenly, the Milky Way wasn't a nebulous mist. It was a stellar metropolis. But how far did it stretch? Galileo had no way to tell. His telescope revealed structure, not scale. The real breakthrough in measuring cosmic distances came not from better lenses, but from a new kind of cosmic yardstick, variable stars. In the late 1800s, astronomers at Harvard College Observatory, many of them women working for pennies, known as computers, began classifying stars from photographic plates. Among them was Henrietta Swan Leavitt. She studied a class of stars in the small Magellanic Cloud, a nearby satellite galaxy, that pulsed with a regular rhythm. They would brighten, then dim, then brighten again over days or weeks. Leavitt noticed something astonishing. The brighter the star appeared, the longer its pulse period. And because all these stars were roughly the same distance from Earth, since they were all in the same cloud, their apparent brightness directly reflected their true brightness. This became known as the period luminosity relationship. It meant that if you found a pulsating star, now called a Cepheidid variable, anywhere in the sky, you could measure how long it took to pulse, calculate its true brightness, compare that to how bright it looked from Earth, and from that difference, determine its distance. It was like seeing a street lamp in the fog. If you know how powerful the bulb is, you can tell how far away it is by how dim it appears. Leavitt's discovery gave astronomers their first reliable standard candle, a beacon whose intrinsic light was known, making it a ruler for the universe. But even with Cepheids, mapping the Milky Way remained maddeningly difficult because we're inside it. Imagine trying to map the layout of a vast forest while standing in the middle of it. Trees block your view in every direction. You can't step back to see the whole shape. That's our situation in the galaxy. Dust, cosmic soot from dead stars, fills the plane of the Milky Way, absorbing visible light and hiding what lies beyond. In the early 1900s, astronomers like Harlow Shapley tried to pierce this veil by studying globular clusters, dense spherical swarms of ancient stars orbiting the galactic center like bees around a hive. Shapley mapped their positions and used Cepheid variables within them to estimate distances. He realized they weren't scattered evenly around the Sun, but clustered in one direction toward the constellation Sagittarius. From this, he made a stunning deduction. The Sun is not at the center of the Milky Way. We're off to the side, about 2/3 of the way out from the middle. This was a second Copernican revolution. Not only is Earth not the center of the solar system, but the Sun isn't the center of the galaxy either. Shapley estimated the Milky Way was about 300,000 light-years across, much too large, as we now know, because he didn't account for how interstellar dust dims starlight, making stars appear farther away than they are. But his core insight was correct. We live in a vast, disc-shaped system, and we're not at its heart. Meanwhile, a parallel mystery was unfolding. Through telescopes, astronomers saw strange, fuzzy patches in the sky called nebulae. Some, like the Orion Nebula, were clearly clouds of gas within our galaxy. But others, spiral-shaped smudges like Andromeda, were enigmatic. Were they small, nearby gas clouds? Or were they island universes, galaxies like our own, far beyond the Milky Way? This question sparked one of the most famous debates in astronomy, the Great Debate of 1920. On one side was Harlow Shapley, arguing that the Milky Way was the entire universe, and spiral nebulae were just forming solar systems within it. On the other was Heber Curtis, who believed those spirals were separate galaxies, each containing billions of stars. The debate ended not with words, but with light. In 1923, Edwin Hubble, using the new 100-inch Hooker telescope atop Mount Wilson in California, spotted a Cepheid variable in the Andromeda Nebula. Using Leavitt's law, he calculated its distance, about 900,000 light-years, later refined to 2.5 million. That was far beyond even Shapley's oversized Milky Way. Andromeda was not part of our galaxy. It was another galaxy entirely. His discovery shattered the cosmic horizon. The universe wasn't just the Milky Way. It was filled with galaxies, each a city of stars. And if Andromeda was that far, then the Milky Way itself must be smaller than Shapley thought. Over the next decades, astronomers refined their measurements. They accounted for dust. They found better standard candles, like RR Lyrae stars, and, later, Type 1a supernovae. They mapped the motions of stars, realizing the galaxy rotates, with inner stars orbiting faster than outer ones. By the mid-20th century, a clearer picture emerged. The Milky Way is a barred spiral galaxy, about 100,000 light-years across, with a central bulge, a thin disk, and spiral arms winding outward. But even then, much remained hidden. Visible light couldn't penetrate the dusty core. It wasn't until the space age, when we launched telescopes that could see in radio waves, infrared, and X-rays, that we began to truly map our galactic home. Radio waves passed through dust like ghosts. In the 1950s, astronomers using radio telescopes detected a strong source of emission at the very center of the galaxy, in Sagittarius. They called it Sagittarius A. Decades later, infrared observations revealed stars whipping around this invisible point at speeds over 5,000 kilometers per second, proof of a supermassive black hole, 4 million times the mass of our Sun, anchoring the Milky Way's heart. Each new tool, each new wavelength of light, revealed another layer. The European Space Agency's Gaia mission, launched in 2013, is now charting the positions, distances, and motions of over 1 billion stars with unprecedented precision. It's like giving the galaxy an MRI scan, tracking how stars move in 3 dimensions, how spiral arms form and dissolve, how the galaxy breathes and evolves over time. But let's not forget where this all began, with people staring up at the night sky, not with instruments, but with wonder. The myths weren't wrong. They were the first maps of meaning. And the measurements, they're the maps of reality. Together, they tell a richer story. Because knowing the Milky Way is 100,000 light-years across isn't just a fact, it's a testament to human persistence. It's the result of generations of observers, thinkers, and dreamers who refused to accept the sky as unknowable. They turned awe into inquiry, mystery into method, and in doing so, gave us a home not just on Earth, but in the cosmos. And yet, even with all our tools, we still can't see the Milky Way from the outside. Every image you've seen of our galaxy, a grand spiral with glowing arms, is an artist's reconstruction based on data from within. We're like fish trying to sketch the ocean. But that hasn't stopped us, because in the end, mapping the Milky Way isn't about getting a perfect photograph. It's about understanding our place in the flow of stars, gas, and time. And that journey, from myth to measurement, is one of the most human stories ever told. In the early years of the 20th century, the universe was a much smaller place, at least in the minds of astronomers. It was generally believed that everything that existed, the stars, the nebulae, the faint smudges of light scattered across the night sky, was contained within a single vast system, the Milky Way. This galaxy, so the thinking went, was the universe. There was nothing beyond it. No other galaxies, no cosmic archipelago, just one island of stars in an otherwise empty sea of space. It was a comforting idea in its way. It kept humanity's cosmic home manageable, knowable, and central. But then came the photographs. Glass plates coated with light-sensitive emulsion, exposed for hours through the giant telescopes of Mount Wilson and Lick Observatory, began to reveal something unsettling. Among the familiar star fields were strange, spiral-shaped objects, faint, ghostly whirlpools of light that defied easy explanation. Some looked like pinwheels frozen in mid-spin. Others resembled cosmic whirlpools, their arms curling inward toward a bright core. Astronomers called them spiral nebulae, lumping them together with glowing clouds like the Orion Nebula, which were clearly part of our own galactic neighborhood. But these spirals were different. They were too symmetrical, too structured, too distant, seeming to be mere gas clouds. The question that began to simmer and then boil was this: are these spiral nebulae within the Milky Way, or are they outside? If they were inside, they might be infant solar systems in the process of formation, as some theorists suggested. But if they were outside, then the Milky Way was not the universe at all. It was just one among countless others. The stakes couldn't have been higher. This wasn't just a technical dispute over distances. It was a philosophical earthquake waiting to happen. It threatened to dethrone humanity not once, but twice. First from the center of the solar system, then from the center of the galaxy, and now possibly from the center of everything. This tension came to a head on the evening of April 26, 1920, in the Grand Lecture Hall of the Smithsonian Museum of Natural History in Washington, D.C. Two of America's leading astronomers faced off in what would become known as the Great Debate, or, more formally, the Shapley-Curtis debate. On one side stood Harlow Shapley, the brilliant, ambitious director of the Harvard College Observatory. On the other, Heber Doost Curtis, a meticulous observer from the Allegheny Observatory in Pennsylvania. Though billed as a debate, it was less a clash of shouts and more a quiet duel of evidence, each man presenting his case with scholarly restraint. But beneath the calm surface, the implications were revolutionary. Shapley argued forcefully that the Milky Way was immense, so vast, in fact, that it had to be the entire universe. He based this on his groundbreaking work with globular clusters, those dense spheres of ancient stars orbiting the galactic center. By mapping their distribution and using Gefiert variable stars to gauge distances, he had concluded that the Sun lay far from the center and that the galaxy stretched some 300,000 light-years across. In such a colossal system, he reasoned, there was simply no room for other galaxies. The spiral nebulae, he claimed, were relatively small, nearby objects, perhaps cosmic whirlpools of gas condensing into stars. He pointed to observations of novae, exploding stars in the Andromeda Nebula. These novae appeared far brighter than those seen in the Milky Way, which Shapley took as proof that Andromeda must be close by. Curtis, however, saw the same data and drew the opposite conclusion. He noted that the novae in Andromeda were too bright. If they were truly similar to Milky Way novae, then Andromeda must be incredibly distant for them to appear so faint. He also observed that spiral nebulae often appeared edge-on, like thin disks, and showed dark lanes that resembled the dust clouds seen in our own galaxy. To Curtis, this suggested they were systems like the Milky Way, viewed from different angles. Most compellingly, he cited the work of Vesto Slipher, who had used spectroscopy to measure the velocities of these spirals. Slipher found that many were moving at astonishing speeds, hundreds or even thousands of kilometers per second, far faster than any known star within the Milky Way. Such velocities made little sense if the spirals were small, local objects. But if they were distant galaxies, their high speeds fit perfectly with a dynamic, expanding universe. The debate ended without a clear victor. The audience was divided. The scientific journals published both arguments, and for several years, the question hung in the balance. What was missing was a definitive measurement, a single, unambiguous piece of evidence that could settle the matter once and for all. That evidence arrived 3 years later, not with fanfare, but with a pencil and a photographic plate. At Mount Wilson Observatory, a young astronomer named Edwin Hubble was systematically studying the Andromeda Nebula, known then as Messier 31, using the world's most powerful telescope, the 100-inch Hooker reflector. Night after night, he compared images taken days apart, searching for changes. On one plate, dated October 5th, 1923, he spotted a faint star near the edge of Andromeda that hadn't been there before. He marked it with a small N for nova and moved on. But when he examined earlier plates, he realized something extraordinary. This nova had actually been visible before, and it was pulsing. It wasn't a nova at all. It was a Cepheid variable star, the very kind Henrietta Leavitt had studied 2 decades earlier. Hubble's heart must have raced. Here, in another galaxy, was a cosmic yardstick. He measured its period, the time between peaks in brightness, and applied Leavitt's period luminosity law. The result was staggering. This Cepheid was far too dim to be anywhere near the Milky Way. Its distance? Roughly 900,000 light-years. Later refinements, accounting for different types of Cepheids, would push it to 2.5 million, but even the initial estimate was enough. Overnight, the universe expanded. Andromeda wasn't a nebula inside our galaxy. It was a galaxy in its own right, a swirling island of perhaps 1 trillion stars, separated from us by an ocean of darkness so vast that light itself took millions of years to cross it. Hubble soon found more Cepheids in Andromeda and in other spirals, confirming the pattern. The spiral nebulae were not clouds, they were galaxies, island universes, as the philosopher Immanuel Kant had speculated over a century earlier, long before anyone had the tools to prove it. The implications were profound. If Andromeda was 2.5 million light-years away, then Shapley's Milky Way, once thought to span 300,000 light-years, was far smaller than he'd believed. Revised estimates placed it at about 100,000 light-years across, a size that made room for countless other galaxies in the cosmos. The universe was not a single galaxy, but a vast expanding archipelago of galaxies, each containing billions or trillions of stars. Humanity's cosmic address had just been downgraded from center of everything to one star among hundreds of billions in one galaxy among hundreds of billions. But the story didn't end there. Hubble's discovery opened a new frontier, measuring the universe itself. In the years that followed, he and his colleague Milton Humason began measuring the distances to more and more galaxies, and comparing those distances to their velocities, as revealed by the redshift of their light. They found a startling pattern. The farther away a galaxy was, the faster it was moving away from us. This became known as Hubble's law, and it provided the first observational evidence that the universe is expanding, a cornerstone of the Big Bang theory. Ironically, Harlow Shapley, who had argued so passionately that the Milky Way was all there was, lived to see his view overturned and to accept it gracefully. He reportedly said upon hearing of Hubble's discovery, "Here is the letter that destroyed my universe." But in truth, it didn't destroy it. It revealed a far grander one. The great debate then was more than a scientific disagreement. It was a turning point in human consciousness. It marked the moment we realized that the cosmos is not just big, it is prolific. That our galaxy is not unique, but typical. That the laws of physics that govern a falling apple on Earth also govern the motion of stars in galaxies millions of light-years away. This unity, the idea that the same rules apply everywhere, is one of the most powerful insights of modern science. And it began with a single question: is that smudge of light part of our home or a home of its own? Today, we know of over 2 trillion galaxies in the observable universe. Each is a self-contained ecosystem of stars, planets, gas, and dark matter bound by gravity and shaped by time. Some are spirals like the Milky Way. Others are elliptical blobs or chaotic train wrecks from galactic collisions. And yet, despite their diversity, they all obey the same cosmic choreography. We understand this not because we visited them, but because we learned to read their light, just as Hubble did, with patience, precision, and a deep trust in the language of physics. But let's return for a moment to the Milky Way itself. Now that we knew it was just one galaxy among many, the question of its size took on new urgency. If other spirals could be measured from the outside, perhaps we could use them as templates to understand our own. Astronomers began comparing the Milky Way to galaxies like Andromeda and Triangulum, studying their structure, mass, and stellar populations. They realized that to truly map our galaxy, we needed to see it not just in visible light, but in wavelengths that could pierce the veil of dust hiding its core. This led to a new era of multi-wavelength astronomy, using radio waves, infrared, and microwaves to peer into regions optical telescopes could never reach. And in doing so, we discovered that the Milky Way is not just a passive island. It's a dynamic, evolving system, swallowing smaller galaxies, birthing stars in its spiral arms, and anchored by a black hole so massive it warps space-time itself. The Great Debate taught us humility, but it also taught us courage, the courage to let go of comfortable illusions in favor of a more complex, more beautiful truth. The universe is not what we thought it was, and that's not a loss, it's a gift. Because every time we expand our map of reality, we expand the realm of what's possible to imagine, to explore, and to understand. The Milky Way may be just one galaxy, but within it lies everything we've ever known, and the seeds of everything we might yet become. For most of human history, we've known the Earth is round, not because we saw it from space, but because we watched ships disappear hull first over the horizon, saw the curve of Earth's shadow on the moon, and measured the angles of stars from different latitudes. We inferred the shape of our planet from clues on its surface. Mapping the Milky Way has been a similar act of cosmic deduction, but far more difficult because we're not just on the surface of a sphere. We're embedded deep within a vast, rotating, three-dimensional structure, shrouded in dust and moving at 500,000 miles per hour around a center we can't even see. If you could magically lift yourself out of the galaxy and look back, what would you see? Not a featureless disk, but a grand spiral, a luminous pinwheel of stars, gas, and dust, with arms curling gracefully outward from a bright central bulge. At the very heart would be a bar-shaped structure of stars, and nestled within that bar, an invisible monster, a supermassive black hole, 4 million times the mass of our Sun, known as Sagittarius A star. Surrounding the disk would be a faint spherical halo of ancient stars and globular clusters, like a crown of fireflies orbiting a lantern. This is our home. But for decades, we had to reconstruct this image without ever seeing it whole, like a painter trying to sketch a cathedral while standing inside one of its pews. The first hints that the Milky Way might be spiral came not from direct observation, but from comparison. Once astronomers accepted that galaxies like Andromeda were island universes, they began studying their shapes in detail. Many, including Andromeda, showed clear spiral patterns, arms winding out from a central hub. In the 1930s and 40s, astronomers like Bertil Lindblad and Jan Oort proposed that our galaxy might share this structure. But how could they prove it? The breakthrough came not from visible light, but from radio waves. In the late 1940s, Dutch astronomer Hendrik van der Hulst predicted that clouds of cold hydrogen gas, the raw material for stars, should emit a faint radio signal at a wavelength of 21 centimeters. This emission, known as the hydrogen line, could pass straight through the dust that blocks visible light. In 1951, teams in the Netherlands, Australia, and the United States independently detected this signal coming from all across the sky. Suddenly, astronomers had a way to see the skeleton of the Milky Way, the distribution of its gas, which traces the spiral arms. By measuring the Doppler shift of this radio emission, how the wavelengths stretched or compressed due to motion, they could also map how the gas was moving. Just as a siren's pitch drops as an ambulance speeds away, light and radio waves from gas moving away from us shifts to longer, redder wavelengths. Gas moving toward us shifts blue. By combining position and velocity data, astronomers like Jan Oort and his colleagues in the Netherlands began to sketch the first crude maps of the Milky Way's spiral structure. What they found was astonishing. The gas wasn't distributed evenly. It was concentrated in distinct bands, arms rotating around the galactic center. But because we're inside the disk, these arms appear to us not as continuous curves, but as overlapping segments, like trying to trace the pattern of a vinyl record while standing on its surface. Over the next few decades, radio telescopes around the world refined this picture, identifying major features: the Norma arm, the Scutum Centaurus arm, the Perseus arm, and the Sagittarius arm. Our Sun, it turned out, sits in a smaller spur between the Sagittarius and Perseus arms, now called the Orion Spur, or local arm, after the constellation where it's most visible. But mapping gas was only part of the story. To truly understand the spiral arms, astronomers needed to track the stars themselves. That's where infrared astronomy changed everything. Infrared light, with its longer wavelengths, slips through interstellar dust almost as easily as radio waves. In the 1990s and 2000s, space-based telescopes like the Spitzer Space Telescope and ground-based surveys like 2MASS, the 2-micron all-sky survey, began peering through the galactic plane in infrared, revealing millions of stars hidden from optical view. These observations confirmed something crucial. The spiral arms aren't fixed structures, like spokes on a wheel. They're more like traffic jams on a circular highway. Stars and gas move in and out of the arms as they orbit the galaxy. The arms themselves are density waves, ripples of higher pressure that compress gas clouds, triggering bursts of star formation. Think of tossing a pebble into a pond. The ripples move outward, but the water molecules mostly bob in place. Similarly, the spiral pattern rotates at a different speed than the stars. This explains why young, bright stars born in the arms are often found just downstream of the densest gas, while older stars, having drifted out, populate the spaces between. This dynamic view resolved a long-standing puzzle. If the galaxy rotates differentially, with inner regions orbiting faster than outer ones, then any rigid spiral pattern should wind up and disappear in just a few 100 million years. But the Milky Way is over 13 billion years old. The fact that we still see spiral arms means they must be transient features, constantly regenerating. The arms are not permanent lanes, but recurring waves of creation. Another surprise came from the galactic center. For decades, astronomers assumed the Milky Way was a simple spiral, like Andromeda. But infrared and radio observations in the 2000s revealed a central bar, a straight, elongated structure of stars stretching about 27,000 light-years across. This made the Milky Way a barred spiral, a common type among galaxies. The bar acts like a cosmic conveyor belt, funneling gas from the outer disk toward the center, feeding star formation and possibly the black hole itself. Simulations show that bars can form naturally, as a galaxy evolves, driven by gravitational instabilities. Ours likely formed billions of years ago and has been shaping the flow of matter ever since. Mapping the full extent of the disk has also been a challenge. The visible stellar disk appears to end around 50,000 light-years from the center. But recent data from the Gaia Space Observatory suggests the stars may extend much farther, perhaps to 60 or even 70,000 light-years, in a flared, warped outer region. This warp is likely the result of gravitational tugs from satellite galaxies like the Large and Small Magellanic Clouds, which orbit the Milky Way like moons. In fact, the Magellanic Clouds are currently pulling on the Milky Way's outer hydrogen disk, creating ripples that extend over 100,000 light-years, far beyond the stellar disk. Even the thickness of the disk varies. Near the center, it's puffed up into a bulge about 10,000 light-years thick. But in the regions where the Sun orbits, about 27,000 light-years from the center, the disk is remarkably thin, only about 1,000 light-years thick. If the Milky Way were the size of a vinyl record, it would be less than a millimeter thick at our location. We're like ants crawling on the edge of a dinner plate, trying to map its entire surface. All of this structure, the arms, the bar, the bulge, the warp, is held together by gravity. But not just the gravity of stars and gas. As we'll explore in the next chapter, most of the Milky Way's mass is invisible, made of something we still don't fully understand: dark matter. Yet, even without seeing it, we can feel its presence in the way stars orbit. The Sun, for example, takes about 230 million years to complete one lap around the galactic center, a period called a cosmic year. Dinosaurs appeared about 1 cosmic year ago. The last time the Sun was in its current position, Earth was ruled by reptiles. Understanding the shape of the Milky Way isn't just academic. It tells us where stars are born, how elements are scattered, and how galaxies evolve over time. The spiral arms are nurseries. Dense clouds of gas collapse under gravity, ignite nuclear fusion, and light up as new stars. Massive stars live fast, die young, and explode as supernovae, seeding the surrounding space with carbon, oxygen, iron, the very stuff of planets and life. We are literally made of stardust forged in these arms. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in stars that lived and died in the Milky Way's spiral currents. And our location matters. Being in a quiet spur, far from the chaotic center, may have been crucial for the development of complex life. Near the core, radiation from supernovae and the black hole would be intense, and stellar densities so high that planetary orbits could be easily disrupted. Out here, in the galactic suburbs, conditions are calmer, more stable, perhaps just right for life to take hold and evolve over billions of years. So when we map the Milky Way's shape, we're not just charting stars, we're tracing the pathways of creation itself. Every spiral arm is a river of potential, every gas cloud a cradle, every supernova a messenger carrying the ingredients of life across the void. The Milky Way isn't a static monument. It's a living, breathing system, constantly recycling matter, reshaping itself and writing the story of which we are a part. And yet, for all our progress, mysteries remain. How many spiral arms does the Milky Way really have? Some maps showed 2 major arms, others suggest 4. Is the local arm just a spur or a full-fledged branch? How exactly does the bar interact with the arms? Missions like Gaia are now providing 3-dimensional positions and velocities for over 1 billion stars, allowing astronomers to simulate the galaxy's dynamics in unprecedented detail. With each new data release, the picture sharpens, not into a final answer, but into a richer, more nuanced story. Because, in the end, the shape of the Milky Way is not just a question of geometry, it's a question of origin, evolution, and destiny. It's the architecture of our cosmic home, and the blueprint for everything that has ever happened within it. To know its form is to begin to understand how we came to be here, on a pale blue dot, orbiting an average star, in one quiet corner of a vast and beautiful spiral. Imagine you're watching a carousel at night. The lights are off, but you can see a few glowing horses near the edge, spinning in the dark. From their motion, their speed, the curve of their path, you try to figure out how big the carousel is, how heavy it is, and what's at its center. At first, everything seems to make sense. The outer horses move slower than the inner ones, just as physics predicts. But then you notice something strange. The horses on the very edge are moving too fast. So fast, in fact, that they should fly off into the darkness. The visible structure, the wooden platform, the central pole, the few lit horses, doesn't have enough mass to hold them in. There must be something else, something you can't see, something massive, hidden in the shadows, holding the whole thing together. This is precisely the puzzle astronomers faced in the mid-20th century, when they began measuring how stars orbit the Milky Way. According to Newton's laws of gravity, and later Einstein's theory of general relativity, the speed at which a star orbits the galactic center should depend on how much mass lies inside its orbit. Stars close to the center, surrounded by dense clusters of stars and gas, should orbit quickly. Stars farther out, where matter is sparse, should move more slowly, just as Pluto crawls around the Sun while Mercury races. This is called Keplerian motion, and it works perfectly in our solar system. But when astronomers like Jan Oort and later Vera Rubin mapped the orbital speeds of stars and gas clouds in the Milky Way and other spiral galaxies, they found something shocking. The rotation curves were flat. Stars at the edge of the disk were orbiting just as fast as those closer in. In the Milky Way, the Sun, located about 27,000 light-years from the center, orbits at roughly 230 kilometers per second. But even stars twice as far out move at nearly the same speed. According to visible matter alone, they should be crawling. Instead, they're racing. And if the galaxy contained only the stars, gas, and dust we can see, these outer stars would have escaped long ago, flung into intergalactic space by their own momentum. The only explanation: there must be far more mass in the galaxy than meets the eye. Not just a little more, but vastly more. This unseen substance doesn't emit light. It doesn't absorb it. It doesn't reflect it. It reveals itself only through gravity. We call it dark matter. The idea wasn't entirely new. As early as 1933, Swiss astronomer Fritz Zwicky had studied the Coma Cluster, a group of galaxies, and found that the visible mass couldn't account for how fast the galaxies were moving. He coined the term Dunkelmaterie, dark matter, but his work was largely ignored for decades. It wasn't until the 1970s, with Vera Rubin's meticulous observations of galaxy rotation curves, that the astronomical community was forced to take dark matter seriously. Rubin showed that flat rotation curves weren't unique to the Milky Way. They were universal. Every spiral galaxy she studied behaved the same way. The implication was inescapable. Galaxies are embedded in massive invisible halos of dark matter, extending far beyond their visible stars. In the Milky Way, this dark matter halo is enormous. While the stellar disk spans about 100,000 light-years, the dark matter halo stretches at least 10 times farther, perhaps as far as 1 million light-years in diameter, and it contains about 5 to 10 times more mass than all the visible matter combined. That means over 85% of the Milky Way's total mass is invisible. We live inside a ghost. But what is dark matter? Despite decades of searching, we still don't know. It's not made of atoms, no protons, neutrons, or electrons. If it were, it would interact with light and show up in our telescopes. Instead, it seems to be a new kind of particle, one that barely interacts with ordinary matter except through gravity. Leading candidates include WIMPs, weakly interacting massive particles, which could be relics from the Big Bang, streaming through space and through us like cosmic neutrinos, but far heavier. Other possibilities include axions, sterile neutrinos, or even primordial black holes. So far, no direct detection has been confirmed, though experiments deep underground and in space continue the hunt. What we do know is how dark matter shapes the Milky Way. Without it, our galaxy couldn't exist in its current form. The visible disk is too thin, too fragile. It would tear itself apart under its own rotation. Dark matter provides the gravitational scaffolding, the invisible skeleton that holds everything together. Simulations of galaxy formation show that in the universe without dark matter, galaxies like the Milky Way simply wouldn't form. Ordinary matter alone, pulled only by its own gravity, wouldn't have come sufficiently after the Big Bang. It was dark matter's gravitational wells that gathered gas, allowed it to cool, and sparked the first stars. Even the Milky Way's history bears the fingerprints of dark matter. Our galaxy hasn't grown in isolation. Over billions of years, it has cannibalized smaller satellite galaxies, dozens of them, perhaps hundreds. We see the remnants today, streams of stars arcing across the sky, like the Sagittarius stream, torn from a dwarf galaxy currently being devoured. These mergers are guided by dark matter. Satellite galaxies orbit within their own dark matter halos, and as they fall toward the Milky Way, gravitational tides strip away their stars, but the dark matter lingers, subtly altering the orbits of stars in our own disk. The Gaia Space Telescope has revealed ripples and waves in the motions of nearby stars, likely scars from past collisions, all choreographed by the unseen hand of dark matter. And then there's the center. At the very heart of the Milky Way lies Sagittarius A star, the supermassive black hole. But even its immense gravity, 4 million solar masses, can't explain the motions of stars in the inner few light-years. Something else is at work. While dark matter is diffuse in the inner galaxy because ordinary matter has collapsed into the disk, pulling dark matter along less efficiently, its overall distribution still influences the global structure. In fact, the shape of the dark matter halo, whether it's spherical, squashed, or slightly lopsided, affects how the visible disk warps and flares at its edges. Perhaps the most profound role of dark matter is in defining the Milky Way's ultimate fate. Right now, our galaxy is on a collision course with Andromeda. In about 4.5 billion years, the two will merge in a slow-motion dance of stars and gas, eventually forming a giant elliptical galaxy nicknamed Milkdromeda. But this merger isn't driven just by the visible mass of the two galaxies. It's orchestrated by their dark matter halos, which are already beginning to interact across the 2.5 million light-year gap. The halos will merge first, their gravity pulling the stellar disks together, like magnets wrapped in fog. So while we can't see dark matter, we live in its embrace. It's the silent architect of our cosmic home. Every time you look up at the Milky Way's band of light, you're seeing only the tip of an iceberg. Beneath that luminous surface lies a vast, invisible ocean of mass shaping, stabilizing, and guiding everything within it. We are like sailors on a ship, aware only of the deck beneath our feet, unaware of the deep currents that carry us across the sea. This realization is both humbling and exhilarating. Humbling because it shows how little of reality we can directly perceive. Exhilarating because it means the universe is far stranger and richer than it appears. Dark matter isn't a gap in our knowledge, it's a doorway. It tells us that the cosmos contains forms of matter and energy we've only begun to imagine. And in trying to understand it, we're not just mapping the Milky Way, we're probing the fundamental nature of reality itself. For now, dark matter remains a mystery. But mysteries are not dead ends, they are invitations. And the Milky Way, with its hidden heart of darkness, is calling us to look deeper, think harder, and dare to believe that the most important things in the universe might be the ones we cannot see. When you look up at the night sky, you are not seeing the universe as it is. You are seeing it as it was. Light, for all its speed, nearly 200,000 miles every second, still takes time to cross the vast distances of space. And in that delay lies a kind of time machine. Every star you see is a ghost from the past. Some are only a few years old in their light. Others are ancient messengers carrying news from epochs before Earth even existed. In the Milky Way, this means we never observe our galaxy in real time. We see it in fragments of history, stitched together from light that left its source decades, centuries, or millennia ago. To map the Milky Way is not just to chart space, it is to reconstruct time. Consider the star Vega, one of the brightest in the summer sky. Its light takes about 25 years to reach us. So when you gaze at Vega tonight, you are seeing it as it was when you were a child, or perhaps before you were born. If something happened to Vega yesterday, a flare, a planet crashing into it, even its sudden death, you wouldn't know for another quarter of a century. The same is true for every point in the galaxy. The farther away an object is, the further back in time we see it. This isn't poetic metaphor, it's physics. And it transforms astronomy into a form of archaeology. Now imagine trying to build a coherent picture of the Milky Way using only these time-delayed snapshots. It's like assembling a film from frames shot at different moments, with no guarantee they belong to the same scene. A star in the Perseus Arm, 20,000 light-years away, shows us what that region looked like when humans were painting caves in Lascaux. A gas cloud near the galactic center, 27,000 light-years distant, reveals conditions from the last ice age. Meanwhile, the Sun's immediate neighborhood, within a few hundred light-years, shows us the galaxy as it was during the Renaissance, the Industrial Revolution, or even last week. We live in a patchwork of eras, all visible at once. This temporal dislocation becomes even more profound when we consider the scale of galactic evolution. The Milky Way is not static. Stars are born, live, and die. Spiral arms wind and unwind. Gas flows inward and outward. The galaxy breathes over millions of years. But human lifespans and even the entire span of recorded history are mere blinks in cosmic time. We cannot watch the Milky Way change in real time. Instead, we infer its life story by comparing regions at different distances and thus different look-back times. It's like walking through a forest and judging the life cycle of trees by seeing saplings, mature oaks, and rotting logs, all at once. From that mosaic, we reconstruct the whole. One of the most powerful examples of this time travel is in the study of star formation. In the Orion Nebula, Just 1,300 light-years away, we see stars being born now, or rather, as they were in the late Middle Ages. Massive clouds of gas collapse under gravity, ignite fusion, and emerge as brilliant young stars surrounded by protoplanetary disks. But if we look toward the Carina Nebula, 7,500 light-years away, we see a more violent, energetic nursery, one that existed when the pyramids were being built. And in the far reaches of the Scutum Centaurus arm, over 30,000 light-years distant, we glimpse star-forming regions as they were when Neanderthals walked the Earth. Each of these snapshots tells us how star formation has changed over time. We see that the rate of new star birth in the Milky Way has slowed. Billions of years ago, the galaxy was a more turbulent place. Gas was denser, collisions more frequent, and star formation rampant. Today, it's relatively quiet. The Sun itself formed about 4.6 billion years ago, during a more active phase. If we could see the entire galaxy as it was then, it would blaze with far more bright, massive stars. Stars that lived fast and died young, seeding the disk with heavy elements that made rocky planets like Earth possible. But time travel in Starlight isn't just about looking outward. It's also about looking inward into the past lives of individual stars. Every star carries a chemical fingerprint imprinted at its birth. By analyzing the composition of the star's atmosphere, its ratios of iron, oxygen, magnesium, and other elements, we can tell how many generations of stars lived and died before it formed. Stars born early in the galaxy's history, like those in the halo and globular clusters, are metal poor. They contain almost nothing but hydrogen and helium, the primordial ingredients of the Big Bang. Later stars, like the Sun, are metal-rich, forged from gas enriched by countless supernovae. This stellar archaeology allows us to date different parts of the Milky Way. The halo is ancient. Its stars formed over 12 billion years ago, when the galaxy was just a chaotic swarm of proto-galactic fragments. The bulge formed next as those fragments merged and collapsed. The thin disk, the home of the spiral arms, came later, as gas settled into a rotating plane and began forming stars in an orderly fashion. And the thick disk, a puffier layer sandwiched between the thin disk and the halo, may be the scar of a major collision early in the galaxy's life, perhaps with a dwarf galaxy named Gaia Enceladus, whose remnants were discovered in Gaia mission data. Even the motion of stars carries echoes of the past. Some stars move in orderly orbits aligned with the disk signs they formed here. Others zip through the galaxy on tilted, eccentric paths like cosmic immigrants. These are likely survivors of swallowed galaxies, their trajectories frozen in time since their home was torn apart. By tracing their paths backward, astronomers can reconstruct ancient mergers, events that happened billions of years ago, but whose consequences still ripple through the Milky Way today. Perhaps the most haunting form of time travel involves the galactic. Center, Sagittarius. A star, our central black hole, is currently quiet, emitting only faint radio waves and occasional X-ray flares. But light from the center takes 27,000 years to reach us. So if a massive star fell into the black hole last week, we won't see the fireworks until the year 29,000. Conversely, any bright outburst we observe today actually happened during the last glacial maximum, when ice sheets covered much of North America and Europe. In fact, there's evidence seen in X-ray echoes bouncing off distant gas clouds that Sagittarius A star was far more active just a few hundred years ago, possibly devouring a large cloud of gas. We're only now seeing the afterglow. This delay also means we can never witness the true present state of the Milky Way. There is no now for the galaxy as a whole. Einstein taught us that simultaneity is relative. There's no universal clock ticking the same for all observers. But even without relativity, the finite speed of light ensures that the Milky Way we observe is a collage of moments, each frozen in the instant its light began its journey to us. And yet, this limitation is also a gift. Because by collecting light from across the galaxy, we gather not just a spatial map, but a timeline. We see the Milky Way not as a single entity, but as a layered history book. Each page written in starlight, each chapter marked by chemical signatures and orbital motions. We read this book not with our eyes alone, but with spectrographs, radio telescopes, and space observatories that decode the messages carried across time. The Gaia mission has turned this time travel into a high-precision science. By measuring the positions, distances, and velocities of over 1 billion stars, Gaia allows astronomers to simulate the Milky Way's past and future with unprecedented accuracy. They can rewind the clock, watching stars trace their paths back to common origins, revealing stellar families torn apart by time. They can fast forward, predicting how the disk will warp, how arms will shift, how the galaxy will respond to the approaching collision with Andromeda. But for all this power, there's a quiet poignancy to cosmic time travel. We are forever separated from the present reality of our galaxy. The stars we love, the familiar constellations, the glowing band of the Milky Way are already different. Some have died, new ones have ignited, spiral arms have shifted, and we won't know for centuries or millennia. We live in the echo of light, surrounded by ghosts of what once was. Yet in that echo, we find connection. When we look at a star 2,000 light years away, we see it as it was when the Roman Empire fell. When we study a globular cluster 50,000 light years distant, we glimpse the universe as it was when modern humans first left Africa. The Milky Way is not just our home in space, it is our home in time. Its light carries the story of cosmic evolution, of element forging, of gravitational dance, and of our own origins. We are made from stardust that was scattered long ago, in places we see only as they were, never as they are. So the next time you stand under a dark sky and see the Milky Way arching overhead, remember you are not just looking out, you are looking back. You are seeing the past breathe. And in that act of seeing, you become part of a story that began long before you and will continue long after, written in light, measured in time, and held together by the silent gravity of a galaxy that is always and never as it seems. There is a moment, quiet, almost imperceptible, when the sheer scale of the Milky Way stops being a number and starts being a feeling. It's not in the textbook diagrams or the glowing simulations. It's not in the data streams from Gaia or the radio whispers from hydrogen clouds. It happens when you stand alone under a truly dark sky, far from city lights, and see the Milky Way not as an object to be studied, but as a presence to be felt. That soft, luminous river arching from horizon to horizon isn't just gas and stars. It's time, it's history, it's the cradle of everything we are. And somewhere in that river, on an unremarkable arm orbiting an average star, is a pale blue dot. Not even a dot really, too small to see, too faint to register. Earth, our home. For all our noise, our wars, our triumphs and tragedies, we occupy less than a speck in a galaxy of hundreds of billions of stars. And yet, within that speck, something extraordinary has happened. Consciousness, curiosity. The ability to look up and ask, what is all this? That alone makes our place in the Milky Way not insignificant, but singular. We've journeyed through the layers of our galactic home, from the human struggle to grasp scale, through the myths that gave the sky meaning to the measurements that revealed its true size. We've seen how the Great Debate shattered the illusion that the Milky Way was all there was, opening the door to a universe teeming with galaxies. We've traced the spiral arms, not as static structures, but as waves of creation, where gas collapses into stars and stars explode into life-giving elements. We felt the pull of the invisible dark matter, the ghostly scaffold that holds the galaxy together, reminding us that most of reality lies beyond our senses. And we traveled through time, seeing the Milky Way, not as it is, but as it was, stitched together from light that left its source before civilizations rose. Now, at the end, we return to the question that started it all: how big is the Milky Way? And the answer is no longer just 100,000 light-years across. It's deeper than that. The Milky Way is big enough to contain every human who ever lived, every thought ever had, every love ever lost, and still have room for billions of years of cosmic evolution before and after. It's big enough to hide its center behind veils of dust, to warp its edges with the gravity of unseen companions, to spin so slowly that a single orbit takes longer than complex life has existed on Earth. It's big enough to humble us, but size alone doesn't define meaning. A desert is vast but empty. An ocean is deep but indifferent. The Milky Way is different. It is not just space. It is a system of transformation. Within its spiral arms, hydrogen forged in the Big Bang is cooked into carbon, oxygen, nitrogen, the building blocks of DNA. In the hearts of massive stars, iron is forged. In their explosive deaths, those elements are scattered across light years, eventually finding their way into clouds that collapse into new stars, new planets, and, on at least one world, new life. We are not separate from the Milky Way. We are its children. The calcium in your bones was made in a star that died before the sun was born. The iron in your blood was forged in a supernova thousands of light years away. You are literally made of recycled stardust, gathered and reassembled by the gravity of this galaxy over billions of years. That realization changes everything. It means that when you look up at the Milky Way, you are not gazing at something outside yourself. You are seeing the extended body of your cosmic ancestry. Every star in that band is a relative, some distant, some closer, all part of the same gravitational family. And our location, 27,000 light-years from the center in the quiet suburbs of the Orion Spur, may not be accidental. Too close to the core, and the radiation from supernovae and the black hole would sterilize planets. Too far out, and there might not be enough heavy elements to build rocky worlds. We live in the galactic Goldilocks zone. Not too hot, not too cold, but just right for life to emerge and persist. This doesn't mean Earth is the only place where life exists. Given the Milky Way's size, hundreds of billions of stars, most with planets, it would be astonishing if we were alone. But even if we are, our existence is a testament to the galaxy's creative power. The Milky Way isn't just a collection of objects. It's a story of collapse and explosion, of chaos and order, of matter learning to reflect upon itself. And we are the part of that story that woke up. There's a temptation, when faced with such scale, to feel small in a way that diminishes us. But the opposite is true. Understanding the Milky Way doesn't shrink our importance. It expands our context. We are not the center of the universe, but we are participants in something vast and beautiful. Our brief flicker of consciousness is part of a 13 billion year cosmic narrative that began with a hot, dense state and led through gravity, nuclear fusion, and chemistry to beings who can map their own galaxy from within. And we've done something remarkable. Trapped inside the disk, blinded by dust, limited by the speed of light, we have still managed to reconstruct the shape, size, and history of our home. We've measured the invisible. We've read the past in Starlight. We've turned myth into measurement without losing the sense of wonder that started it all. That is not just science. It's a deeply human act, a refusal to accept mystery as final, a commitment to seek truth even when it's hidden. As we look to the future, the Milky Way continues to evolve. In 4.5 billion years, it will merge with Andromeda. The night sky will transform. New stars will ignite in the chaos. The sun, by then a red giant, may have already consumed Earth. But the atoms that made us will still be out there, drifting through the merged galaxy, waiting to be part of something new. The story doesn't end with us, it flows on. But for now, in this fleeting moment of cosmic time, we have the rare privilege of knowing where we are, not just on a map, but in the grand arc of matter and time. We are stardust that has learned to wonder. We are the Milky Way, looking back at itself. So the next time you see that faint band of light across the sky, whether from a mountaintop, a desert, or a memory of a darker world, don't just see stars. See the river that carried you here. See the forge that made you. See the home that holds you, not as a prisoner of scale, but as a participant in a story so vast, so ancient, and so full of potential that it took 13 billion years just to produce someone who could ask, how big is it? And in asking, begin to understand. The Milky Way is not just big, it is the stage, the script, and the audience. And we, every one of us, are part of its light.